Hello and welcome to Lecture 4 of Circular Motion in Phys 1104. This lecture is going to be about forces on objects in circular motion, but we've actually already seen everything we need to know, so I'm just going to use this lecture to work a couple of examples. First, I'm going to analyze this motion of the ball swinging around on the end of the string. So just a rough measurement on the screen has told me that this string is at about a 30-degree angle, and I timed the revolutions and found that the period is about 1.1 seconds. And I'm going to show that we can determine the length of the string. Now this may seem like rather an odd way to determine the length of the string. Why don't I just go back to the lab and measure it? But what this shows is that dynamics of situations like this allow you to determine the scale of an object just by carrying out analysis of the motion. So I'm going to start with a free body diagram of the ball. So we know that there must be a gravitational force, and the only other force that can act on it would be a force due to the string. And we know that the acceleration has to be into the center of the circle. So I've drawn this free body diagram exactly in the perspective in the picture, with the ball coming out of the page at us and the center of the circle to the right. So now I'm going to write the equation of motion. First, let me do the trigonometry. So I'm going to do the analysis of this force. I'm going to work with axes that are upright, like so, and split the force due to the string into its components. And I can see from the triangle that the x component is going to be the magnitude times cos theta, or 30 degrees, and so the other one must be sine. And so now I can write my force sums. The only x component of any force here is the x component of the force due to the string. And so that equals max. Well, this is circular motion. This is uniform circular motion, so the acceleration is directly into the center, and we know that that is parallel to our x-axis. So this is just the magnitude of a, and for circular motion we know that's v squared over r. And then I can write the y component sum, and I can see that the y component of this acceleration is 0. Let me just count my unknowns. I have the force due to the string as one unknown, and I have r as another unknown, and I have v as another unknown. So at the moment, there's no point really doing any algebra because I can't possibly solve this. But there is something else I know. I know that v is the circumference divided by the period. And I know the period. So this has added no new unknowns because I already had v and r as unknowns. So now I have 3 equations in 3 unknowns, and I can solve. So I'm going to start by eliminating the force due to the string, the magnitude. Out of the y component here, I can just solve for it. And then I'm going to use that to eliminate it from the x component equation, and at the same time I'm going to substitute in for v. So my x component equation becomes this. And I can solve that for r, because r is the only unknown left in it. So I'm just going to solve this equation for r now. I'm going to note that cosine over sine is cotangent. If you didn't see that, no big deal, but it does allow me to slightly simplify this expression. I'm just going to do a quick unit check. I have g times a time squared And so that comes out as meters, as it should. And plugging all the numbers into my calculator, I get 53 centimeters. And looking at the picture and comparing the length of the string with the length of my arm, or rather comparing this radius with the length of my arm, that's perfectly reasonable. I can now get the length of the string from the fact that r is just L cosine 30 degrees. And so I could now use this to get the length of the string. But I'm going to say with this, we're done. So now let's work a non-uniform circular motion problem. Here's a car, and it starts at rest here on the x-axis, and it speeds up at a constant rate going around this circle, so that the next time it crosses the x-axis, it's going 25 meters per second. Now notice something. The rate of change of speed is constant. However, the acceleration is not constant. Not even the magnitude of acceleration is constant, because the radial part of it depends on speed. What we do know is that at this moment, the acceleration must be inward and forward, so perhaps at some angle like this. And that is going to split into a radial part and a tangential part. And we're going to find the sizes of those, because that's what's going to tell us what the static friction is. Think about a free body diagram of this. Now, I'm not going to do the usual thing we do in uniform circular motion and draw the free body diagram with the car coming out of the page at us, because that wouldn't put the acceleration in the plane of the page. So I really don't have much choice here but to draw it from above with the static friction acting this way. And I'll simply note that the only other forces on it are a gravitational force and a perpendicular force, which are perpendicular to the page. And so I can't really draw them. But that doesn't matter. We know that they add up to 0. All we care about is this static friction. And it is in the direction of the acceleration and is in fact the whole cause of the acceleration. So if we can find the acceleration, we can find this force. One other thing we'll need to know is the inertia of the car. Let's say it's 1,000 kilograms. And we now have everything we need to know to find this static friction. So I'm simply going to find the acceleration, because I then know that the static friction, in fact, in this case, equals ma, because these two forces cancel each other out. So all that's left is to find the acceleration. Well, that's actually going to be relatively simple. At this moment, we know the speed, and so we know that the radial acceleration is just v squared over r, or so all that's left is to find the tangential acceleration. Now note that the tangential acceleration is directly related to the angular acceleration. And we have enough information to figure out the angular acceleration. We know that our final angular velocity is just v over r, vf over r. And so, and note that the meters cancel, and so this has units of inverse seconds, but we have to interpret that as radians per second. Remember, radians are unitless, and so they don't usually show up in your calculations. But we know that from the way we did this, we're getting an angular velocity in radians per second. And we know that the initial angular velocity was 0. And we know that our delta theta was a full circle. Well, I hope you know that there are 2 pi radians in a circle. If not, you can just note that the arc length is r theta, and so if the arc length is the full circumference, which is 2 pi r, then that's r theta, and so that tells you that there are 2 pi radians in a circle. Well, so now we can find the acceleration because we have a uniformly angularly accelerated motion equation. And so this gets us alpha. And so then what we really want is the tangential acceleration, which is just r times this. And that is about 0.5 meters per second squared. And so I now know the whole acceleration. In my coordinate system, the x component is negative. And so I can just write in total the acceleration, which I know has a negative x component and a positive y component. The radial part is giving me my x component here. And the tangential part is giving me my y component. And now to get this static friction, all I have to do is multiply all of that by 1,000 kilograms, and I am done.